Hello, this is a talk I held at the Embedded World Conference in Nuremberg on data-centric programming, modular programming in C++, and how a number of techniques can be joined together to realize a system of code building blocks. This system then consists of code blocks and graphical controls, which can be configured into an application without compilation. The contents are a sort of very fast forward of steps in software architecture that I have taken over a number of years. These steps started with data-centric programming, which in combination with strict modularization went on to object-oriented programming. The runtime configurability is then achieved by turning classes into building blocks that publish their inputs and outputs to a building block framework. Finally, I'll show you a quick demo and how it's created on the fly. Let's start with data-centric programming. First of all, there is an empty box of code. Then a so-called data object is created with a call to create DO. The data object, or short DO, is represented by the yellow box. As shown in the bubble, it consists of a little memory space, like a dynamically allocated variable. Attached to this DO are lists of callbacks, one list for each configured priority of the system. Initially, these lists are empty. Let's write a subscriber function called onFastReact. A subscriber function is a callback function that gets called by the system. One parameter of the function is a new value of a DO. The subscriber function can be registered with any data object. The call to addNotifyCB registers the subscriber function onFastReact with the just created DO at priority 0, which is the highest priority. The data-centric operating system, or DCOS, will from now on take care that whenever the DO changes, onFastReact gets called as soon as possible. Here we see how onFastReact actually gets added to the callback list of the DO. This is an implementation detail really, but it may help the more technically minded of us to understand what's going on in the background. Now I add a few more subscribers for the same data object. Finally, I set the DO to the value of 5. The colored arrows popping up symbolize how all subscribers are being called in the order of their priority. High priority is red, the medium is blue, and the low priority is drawn as a black arrow. Before I start making the application more complex, I want to hide an implementation detail. Now I add more data objects and subscribers to create a more complex system. The broken line means that the subscriber functions calculate new values of another data object. Dynamically changing data can also be shown and edited on a graphical user interface by linking it to standard controls. Before carrying on, I want to briefly summarize the features of data-centric programming as discussed so far. The data object is a thing with a value that is able to notify other entities, namely the subscribers, of its own change. In a system of such data objects and subscribers, the data triggers itself through an application. As a result, the reaction will always be as fast as possible for a given priority. Subscriber functions are callback functions that receive new data through a parameter passed into the function call. A common programming paradigm uses loops and polls for changes. This wastes processing time if things have not changed. Another direct consequence of this programming paradigm is the introduction of jitter, when various cycles run simultaneously. Both effects are avoided when using data-centric programming. The implementation of the DCOS on, for example, a Cortex M3 uses the interrupt controller to assist priority scheduling. As a result, the reaction time is around 10 to 20 microseconds. This is considerably faster than a context switch can be achieved on an application processor with a full-blown RTOS. Multi-threaded programming usually involves mutexes, etc., to synchronize access to resources used across several threads. This adds complexity because it quickly becomes very difficult to determine which resources are being used by which threads. The DCOS does the synchronization for you, and it passes safe copies of data objects values into the subscribers. It thereby avoids a lot of complexity usually involved with multi-threaded programming. At the same time, it avoids the overhead that is associated with using synchronization functions. Again, this saves performance. Now let's move on to data-centric programming in C modules. Here we have the same image as we had before. This may just about be done in a single main file, but it starts getting messy, so let's start to re-establish a little more order by separating things into C modules. The first module is responsible for accessing the hardware registers and for retrieving a value, for example from an AD converter. It sets the AD value to a data object. This is a well-described task, and any source code required to do this job belongs into a single C module. This could be an ADC module. The other modules all have their own job to do as well. There also is a separate module for the GUI and another one for sending data away on a bus. Another module realizes a hardware reaction. This module consumes data only. Other modules are often platform and hardware independent, like modules 2 and 4. They are often mere logic modules that operate on incoming data to produce new outgoing data. Modules take input or produce output or both. Next slide. Again, I start with the result of the previous page. To look at a module's implementation, I want to concentrate on a few modules only. And I also want to deal with the data links later. Here we see what the essential part of the module's headers could look like. All modules have an initialization function. Module 1 publishes the ID of its outgoing data object. This can be thought of as a handle that is used to reference the data object. Module 2 also has such a data object ID. Because it also takes input, a subscriber function is being declared too. Module 3 takes input only and therefore has a subscriber function on XX React, but no data object ID. Function main calls the initialization functions of all modules, and it adds the data links from a module's outgoing data object to another module's input subscriber callback functions. In summary, the modular data-centric programming reduces complexity because no module knows anything about any other module, and the modules can easily be isolated, stress tested, and be reused in different contexts. Main.c, or CPP, knows all modules and is the central switchboard that links all modules' outputs to inputs and thereby spans up the whole application. Before proceeding to object-oriented data-centric programming, I want to recap from a software architectural perspective what we have so far and what we're about to do next. So far, by writing the source code of a module, I decided which modules exist in an application. Even though very similar, I had to write separate source code for timer 0 and again for timer 1. From now on, the module will be changed to a class, and only the function main will determine how many, if any, instances of available classes will exist in a project. While before the existing source code and the linker decided what exists, from now on the existing source code and the linker decide what is available. Only the number of constructor calls from main decide what really comes into existence. Here are the modules turned into classes again. What are the difference to what we had before? Instead of a module init function, Each class now has a constructor which creates the instance. Apart from a few other mere syntactic changes, this looks pretty much the same. Only the subscriber callbacks need an additional instance pointer. And we can have multiple instances of each class, reusing just one chunk of source code for a whole set of peripherals like timer 0, 1 and 2. Now here's a summary of migration to C++. How does the object orientation help? There is a single set of source code for many principally identical things. These things typically are hardware peripherals or logical operations. So we save a lot of ROM footprint. The added indirections of an added this pointer cost very little performance only. I measured this in my 2008 presentation I held at the Embedded World Conference.